Okay, so we're going to be tackling 8.8 next. So the main conditions are going to be that P and Q are conjugate exponents with F in LP and G in LQ. Then we're going to start with three statements. The fourth one comes at the end. First, the convolution of F and G exists for all X. 2, the convolution of F and G is bounded and uniformly continuous. And 3, in the uniform norm, the convolution of F and G is always less than or equal to the P norm of F times the Q norm of G. So real quick, we remember Holder's identity is this guy here from before. We have that, so if we fix any X, we're going to start with number 2. If we fix X, then we have the statement that the convolution of F and G of X, absolute value of it, is this by definition. However, here we can pull the X out using the, by composing it with the translation with respect to X. Again, this integral is with respect to Y, so we can pull out X as if it's a translation, not to mention we fix X here. So from there, we get that the integral tau X, composition F negative Y, Gy, dy, is going to be less than if we took the absolute value on the inside first, because you have the integral of the absolute value is always going to be greater than the standard interval, or the standard integral. Then we notice that this is exactly what is meant by the one norm of T compose X F negative Y times Gy. So then we get that this is going to be less than the product of this guy in the LP norm times the product of this in the Q norm. Now, we've already showed that tau X is translation invariant. So, norms are translation invariant. So we drop that when we get here, and we get our inequality straight out because the negative is going to do nothing with respect to the norm. So the one note is that here's where we note that this is in fact in LP, so we can do this. We can follow directly from Holder's inequality. Now, what this gives us is that F is bounded for all X. Now, if this thing is bounded for all X, then it's bounded for all X by this product that gives us that it also exists for all X. So we've now knocked out 1 in the first part of 2. Now we need uniform continuity. And we're going to use the boundedness for this. So we're going to consider a translation Y. We're going to consider the translation Y of F convolution G minus F convolution G within the uniform norm. Again, if you have, what we need to show is if it's uniform continuous, we need to show it's continuous with respect to the uniform norm. So what we're going to do is we're going to turn this into the convolution of, the translation of F minus F. We're going to factor out the G and end up with the convolution with respect to G. And then because, convolution of this with G, and because this is bounded, we know that it's equal to the infinity norm, because the infinity norm is what it's bounded under almost everywhere. So if the function is purely bounded, these two are going to be equivalent. Then, from here, we expand this guy, and we notice that the, one second. What did I do? Right, then we do the same trick again where we take the translation with respect to X out. So we pull out that. Now we just have this of Z, sorry, it should be an of Z there, of Z, GZ, and then this here is again less than the absolute value of that. So we can now do the same trick that we did up here using Holder's identity to pull this out and show that it is less than these two guys inside of the infinity norm, right? Because we still have this thing surrounded by our infinity norm. But now what I have is that with respect to the P norm, T the translation of yf minus f times the translation of g in the q norm, both of these are constants. So I can pull them out of the infinity norm, or I can just drop the infinity norm, and I'm left with this statement here. Now, proposition 8.5 from the section before tells us that, again, translations are continuous with respect to the p norm. So we get that this guy here is going to 0 as y goes to 0. So this gives us that it's continuous with respect to the uniform norm, which tells us that it's uniformly continuous. So we've got 1 and 2 checked off. What we have left is number 3. Number 3, 1 second, is on the next board. So what we want to show is this inequality here, so that in fact the convolution of f and g in the uniform norm is less than these guys. So we're going to start with this. We're going to expand again, doing the same trick where we pull out tau of x there. Then we say that this is the same thing. Again, this is going to be less than if we do the absolute values. We use the same trick again with Holder's identity to get this guy here with respect to the uniform norm. But now both of these are constants again. So just like when we pulled it out of the infinity norm, here we can pull it out of the uniform norm, or drop the uniform norm. And then we're left with simply that f, p, and g is greater than the uniform norm of the convolution. It's basically the same argument as before, but instead of using turning the uniform norm into showing it's equal to the infinity norm, we just directly do it because we don't need the argument from before. So, or sorry, because we're not trying to show continuity, right? We're not going to end up trying to take the limit. So what we have next is the fourth part of the proposition, and that's going to be that if p and q are both finite, then the convolution is in C0Rn. Now, I'm going to write out, I wrote a proposition 4.35, which is what we're going to do to show this. And I also wrote the definition of C0x and C sub c of x. So the proposition is if x is a locally compact Hausdorff space, which in our case we're working in Rn, so it is a locally compact Hausdorff space, then C0 of x is equal to the closure of Cc of x in the uniform metric. Now, C0 of x is the set of all functions who disappear at, or who vanish at infinity. And what this means is that if you take the set of all x's for which f of x is greater than epsilon, this set is going to be compact, and this is true for all epsilon. So another way to say this is that in our case in Rn, if you take the function, the set of all points that f map over epsilon, that is going to be compact, which means bounded and closed and bounded. So what we're going to get there is that for every epsilon, f outside of some circle around the origin is less than epsilon. So as you go further and further out in Rn, f vanishes to 0. Then c sub c is that instead of f vanishing at 0, going down to 0 as it goes out to infinity, it actually hits 0 at some point and keeps going out. So we have that all the values of x such that f of x is not 0. So all the non-zero values of the function form a compact set. And again, in Rn, this is going to mean closed and bounded. So there is some value that you can pick in R such that the ball around the origin of that size contains all the non-zero values of the function. So the function is 0 everywhere, but at some finite sphere of points. So what we want to show is that since we're trying to show that the convolution of f and g is always going to be in C0 of x, we need to show that we're going to use proposition 4.35, which says that C0 of x is the closure of C sub c of x. So what we're going to do is we're going to take two sequences, fn and gn in CC, such that fn goes to f and gn goes to g. And again, we know that this is possible because f and g live in LP and LQ, so we're working in Rn, so we know that they can't be arbitrarily large, arbitrarily far out in Rn. So we know that there's going to be some sequences of this form that that approach these two functions, right? With respect to the p norm and with respect to the q norm for fn and for gn. So what we're then going to use is proposition 8.6d, which is what we used last time, which said that the convolution, that the support of the convolution of two functions is contained in the closure of the Minkowski sum of their supports. And if you take the Minkowski sum of two compact bounded sets, you're going to get a compact bounded set. So you've got that this guy is living in a subset of a compact bounded set, which means that we know that it is bounded, and we get compactness from the fact that the Minkowski sum of compact sets is compact. So we get from here, what we want to do is we want to show that within the uniform norm, the convolution of these two sequences goes to the convolution of f and g. And the way that we're going to do that, the book just writes this inequality, which took me a few minutes to figure out. So I wrote out in a lot more detail the steps. So the book just goes, oh yeah, it's less than this thing. And then goes, and this thing is obviously going to 0. Because this guy here by assumption was going to 0, and this guy here by assumption was going to 0. So we get that the sum of the products is going to 0. Now, the question is, why is this inequality true? So what we're going to do is we're going to start by writing these out as integrals, and then combining them because integrals are linear, so I can slap the difference of them between. So I've got the integral of fn x minus y gn y minus fx and x minus y gy dy. And again, this is within the uniform norm. So, there's, you guys see that? Is that better? No. Let me just turn this light off. There we go. Okay. So, slide this guy down. Try to make everything a little more centered. So, what we have, so we just expand this guy using the integrals and then put them together into one. Then we're going to subtract gny fx minus y and add gny f of x minus y. So we subtract this here, add it there, right? Now we can factor. So we're going to factor the gny out here. So we're going to get gny times fn x minus y and where is it? Fn x minus y and f of x minus y here, right? So we factor that guy out. Then we're going to do the same thing for the other one, get gny minus gy times f x minus y. Now, because we have a sum, we can just use the sublinearity of the norm to split this into two separate norms. So this is going to be less than if I had this as two separate norms, u and u. right? Now we can use, we know that gn minus y still lives in LQ, and we know obviously F lives in LP, so we can apply Holder's inequality to this norm, and we can apply it to this norm. So we're going to get that this is less than or equal to these two products, which is what we had here. And then again, these both go to 0 because of our assumption that the sequences converge to 0 in the first place, or converge to F and G in the first place. So that does it for 8.8. 8.9 up next. I will see you guys in a bit.